So in today's video we're going to learn about two functional groups called aldehyde and ketone, and we're going to learn about what are their properties, how the functional group looks like, and what are the chemical reaction both of these groups normally show. So let's start with the group called carbonyl group, because aldehyde and ketone contain the carbonyl group, and this carbonyl functional group is the characteristic of both aldehyde and ketone. So what is carbonyl group? Carbonyl group is a double bonded, carbon is double bonded to an oxygen atom. If you can see over here, you have carbon atom that is double bonded to the oxygen atom, and then you have one single bond across the carbon. So so we're gonna see how this carbonyl group is different in aldehyde and ketone. So in aldehyde, in a carbonyl group, if you have two bonds, one of the bond is attached to the R group and second bond is attached to the hydrogen atom in aldehyde. So if you can see over here, this is a carbonyl group, and then in one of the bond you have hydrogen atom, and the other bond you will have an R group. An R group can be an alkyl group, right, or any carbon group, right? Whereas in ketone, for on carbonyl group you will have two carbon atom attached to adjacent to the carbonyl group. If you can see, if you have a carbonyl group, you have carbon atom on both sides of this carbonyl group, and this group together we call as ketone. So make sure you know the difference between the aldehyde functional group and ketone group, and you need to know how does it different, because both of them has a carbonyl group. So the only difference is in aldehyde you have an hydrogen atom in one of the bond, and in ketone you will have carbon atom attached to both of the bond on the carbonyl group, carbon atom. So now let's see or learn how to name an aldehyde. So we already know how does the aldehyde looks like. Aldehyde is always R with a carbonyl group C double bond O, and then you will have H at the end. So this is your aldehyde group, right? So if you find any this group in any of the hydrocarbons or any organic compound, that's mean we are talking about an aldehyde. So for to name any aldehyde molecules, the rule will be the same that we have been discussing since the hydrocarbons part, the alkane, alkene and alkyne or alcohol, exactly the same. You have to follow the same rule, but the only difference is over here, if you have an aldehyde group attached to or is present in an organic compound, you have to give the preference to the aldehyde group, that functional group. You have to give the lowest number possible to that aldehyde group carbon. So let's take an example. So this is the example that we're going to talk about. So we have how many carbon in this entire molecule? We have 1, 2, 3, 4. We have 4 carbon, but which end we have to start counting? So we have to give the preference to the aldehyde group, which is this. So we have to give the preference to this carbon that has the aldehyde, that carbonyl group, right? So 1, 2, 3, 4. So we have total of 4. On the third group we have bromine as your substituent, right? So the name will be 3-bromo. On the third you have bromo, you have 4 carbon, butane, and then at the end you always end with Al. So the ending word for an aldehyde molecule will always be Al. That's why we have 3-bromo, 4 carbon is butane, and the ending word is Al, butanol. Similarly, let's take this example. So we have 1, 2, 3, 4, 5, total of 6 carbon, but we have to see how to figure it out the parent chain. So to make a parent chain, you make sure you have to include the carbon the carbon that belongs to aldehyde in your parent chain. You have to give the preference to the aldehyde molecule or aldehyde functional group. So in this case, you have to give this preference to the aldehyde the aldehyde group, which is 1. Then you have to go this group down 2. Now you have a choice, either you can go left or you can go right to calculate how many carbon you can have in your parent chain. So in this particular case it doesn't matter, because if you go left you will have 4 carbon altogether. If you would have gone right, still 4. So it doesn't matter in this particular group. So let's let's go to the right. So this is your parent chain. Right, and how many carbon you have in the parent chain? Again 4. And this will be your substituent. This 2 carbon chain is your substituent. Right. And then you have 2 carbon, means this is ethyl. Right, so the name will be, on the second carbon of the parent chain you have ethine molecule attached as a substituent, so that means 2 ethyl. How many carbon total in your parent chain? 4. 4 is butane, and the ending word will be Al, so 2 ethyl butanol. Right. So let's go to the next. So let's do a couple of examples how to name an aldehyde, whatever we learned in the previous slide. So the question is saying name the following aldehyde according to the IUPAC system. So the first you need to know, the time you see this functional group, we know this is an aldehyde. So you need to know how does the aldehyde looks like. That's very important. So first you need to know the functional group. So let's do the first question over here. A, what should be the name? You have to give the preference to the carbon of the aldehyde group. So this is your 1, 2, 3, 4. Again 4 carbon. 4 carbon is butane. Because this is aldehyde, I can write butanol, or I can say 1-butanol. So again, if you don't want to write 1, is it still okay? Because if you don't write anything, that means we are assuming that the aldehyde group is present on the first carbon, and it always will be the case, because the aldehyde group, the carbonyl group in the aldehyde will always be a corner carbon, because the other bond is always attached to the hydrogen. So in aldehyde, if you have aldehyde group in any hydrocarbon, that group should always be a corner carbon, so that you can start counting that carbon as number 1 always. Let's start with the second B option or B question. Again you have an aldehyde group. Give the preference to aldehyde group 1, 2, 3, 4. Again, what's the name? So on the third carbon you have bromo, and you have altogether a 4 carbon, 3 bromo, butanol. What about C? Again 1, 2, 3, 4. This is your parent chain. That's your substituent. You have 2 carbon in your substituent is 2-ethyl butanol. Right. So let's try to do some more example on this aldehyde, and then we'll go to the ketone. So these are the solution of the previous problem that we already done, all the 3 problems. So you can have a look and see how we normally solve, but I already explained to you how to name all those molecules. So again, this is the same. So let's try to solve a couple of more problem on aldehyde. So let's try to solve one. So this is one of the problem that we're going to solve. Second, and then this is the third. Okay, so let's try to solve all these 3 problems that I just drew. So let's start with the first one. Okay, So this is a line angle formula, and then we have to make sure you know how to figure it out whether which functional group you have, right? So the time you see C double bond O over here, and so that we know this is an aldehyde group, because this is carbon, this is C double bond O, so you should have at least one hydrogen on this carbon to make that carbon 4 bonded, right? 4 bond on this carbon. So this is an aldehyde group. So once we figure out which functional group you have, then we have to just follow exactly the same rule. So let's start with this carbon, the carbonyl group of the aldehyde. Let's give it number 1, 2, 3, 4, 5. Now you have an option. You can go straight 6, 7, or you can go up 6, 7. So in this case it doesn't matter, because after 5, if you go either end on, like, doesn't matter which end, which way you're gonna go, both you will have 2 more carbons, so that means total of 7. So I would just go straight. So this will be your parent chain, right? And then this is a substituent, and in substituent how many carbon you have? You have 2 carbons, so this is your ethyl group. So how are we going to name this molecule? We're going to name 5-ethyl, and we have 7 altogether. That's why we have heptanyl, Al, right? Because this is an aldehyde. So 5-ethyl heptanyl. So let's try to do now the second one. So again you have an aldehyde group over here. So you always have to give the preference to the aldehyde 1, 2, 3, 4, right? And then this is 5. So it doesn't matter if I go up or down, both has just 1 extra carbon again. So you have total of 5. So this will be your parent chain. But in this particular case, you have 2 substituents. One of the substituent is this, which is methyl. Another substituent is this, which is hanging from the parent chain. This is your methyl. So I can write the name for this molecule as 3,4 di, because we have 2 same substituent, dimethyl, and then we have 5 carbon all together, that means pentanyl. So this is 3,4 dimethyl pentanyl. So let's go for the third one. So this problem is a little bit different than the previous two, because in this case we have what? We have a benzene ring. So this is a benzene ring. So this is an aromatic compound. If you have an aldehyde group, on a benzene, then we normally call that particular compound as benzaldehyde. Right? So this is benzaldehyde. So let's try to do one more question on the same concept of benzaldehyde. Let me give you the fourth question over here. So if you have benzene, if you have an aldehyde on benzene, and if you have this chlorine atom attached to the benzene ring, how are you going to name this thing? So it's again the same concept. The time you see benzene along with an aldehyde, you know this is benzaldehyde, right? And you have to give the preference to the carbon that contain the aldehyde group, right? So this is the number 1 carbon. Make sure you don't give the whenever you're working with an benzene group, make sure you give the preference or start counting the carbon on the benzene. You cannot start counting from the carbon of the aldehyde group. You cannot do this thing. So make sure you don't do this mistake. So always give the number to the carbon on the benzene ring. So this is 1. Then you have to give the preference to the substituent. Then 3, then 4, 5, 6. So again I am saying, if you can see, I didn't start from the carbon of the aldehyde. I give the preference to the carbon on the benzene ring. So make sure you remember this thing. So what should be the name? The name will be 2-chloro, then benzaldehyde. Right, so this is the name of this molecule. Right. So make sure you practice all this type of question. So let's go to the next slide. Now let's try to how to name a ketone, the functional group ketone, if you have any functional group in the organic compound. So what is ketone? Ketone is a carbonyl group with, on both sides of the carbonyl group you have carbon atom, right? That's your ketone. So again the same rule, but you have to just figure it out the functional group in the organic compound before you name. So let's try a couple of example over here, and again the same rule, you have to give the preference to the ketone or the carbonyl group of the ketone. You have to give the preference to the carbonyl group of ketone or just ketone. So if you can see from this ketone structure, is it possible for ketone, the carbonyl group of the ketone, to be on the corner of the organic compound? No, because always whenever you find a ketone functional group in a compound, it always be the second or more than that. It should not be present on the corners carbon, right? So make sure you know the difference. So let's compare the aldehyde group, right? Just to have a comparison. This is your aldehyde. This is your aldehyde. And this is your ketone with C double bond. That's your ketone. COC, right? Or you can say COC bond. So if you can see, aldehyde, the carbonyl group in the aldehyde is present on the corner because you have hydrogen atom on the other side. But the carbonyl group in ketone cannot be present at the corner of the organic compound because both sides is covered by carbons, right? So make sure you know the difference. So let's start with a couple of examples. So let's do the first example over here. So this is the carbonyl group. The time I see the carbonyl group, we know this can be an aldehyde or ketone. But how would you know this is a ketone? Because on both sides of the carbonyl group you have carbon atom, right? So this is a ketone molecule. So how are we going to name the ketone molecule? You have to start from the corner carbon. You cannot start from this carbon, right? So you always have to start from the corner, and you have to give the lowest number to the carbonyl group of the ketone. So if I will start from here, the second carbon is going to be a carbonyl group of the ketone. So that's why we're going to start from here. Then we have 3, and if I go down, we have just 4. So that's why I'm not going down over here. I have to go straight. 4, 5. So how many carbon we have in total in our parent chain? We have 5 carbon, and this is the carbon that is act as a substituent. So how we name it? 3-methyl. On the third carbon you have methyl group, and the carbonyl group is present on which carbon for the ketone? On the second carbon. So that's why we have 2 pentane, because we have 5, and if you can see, the ending word is ONE. So remember this thing, whenever you're naming any ketone, the ending word will always be the ONE, right? Pentanone, hexanone, right? ONE. So make sure you remember this thing. So and should be ONE, right? Okay. Let's try to do the second problem over here. As we know, this compound is a cyclic compound because this is closed ring all the way, and you have C double bond O over here. So is it a aldehyde group, or the carbonyl group belongs to the aldehyde, or a carbonyl group belongs to the ketone? You have to figure it out. So how are we going to figure it out? The time I see this carbon, and that contains C double bond O, and then on both sides of this carbon is also a carbon. So we know this is a ketone group, right? If it was an aldehyde, then one of the ends should be containing a hydrogen atom, right? So this is a ketone. So that's how we normally decide whether it's a ketone or aldehyde. So again, give the preference to the carbon that has C double bond O. This is the first carbon. So why we are putting a number 1 on the carbonyl group over here, but in this case we didn't put our number 1 on the carbonyl group, because in a cyclic compound each of the carbon is same. There is no like corner carbon, no ending carbon, so every carbon is same. So that's why in a cyclic compound we always have to give the number 1 to the carbon that has a carbonyl group, right? Because there is no you cannot say which carbon is corner carbon and then you can start. So make sure you know this thing. So this is 1, this is second, you have to give the second priority to the preference, then 3, 4, 5 and 6. So what should be the name? On the second carbon you have methyl group as a substituent, so 2-methyl, and because this is a cyclic compound, that's why we have to write cyclo. So make sure you know we already covered this in alkane, cycloalkane. And then how many carbon you have in the cyclo compound? 6. So 6 is hexane, and you have a ketone group, that's why we are writing ONA. So that name will be 2-methyl cyclo, because it's a cyclic compound, and hexanone. So this is how you normally name any cyclic compound. So now let's try to do naming for some ketone by using the same rule. Let's try to give the IP name of the following ketone. So how we can number it? 1, 2, 3, or you can go 1, 2, 3. Doesn't matter in this case because the carbonyl group is getting the second number, right? The lowest number, it can be a second, so it doesn't matter for this particular compound. So the name will be, how many carbon you have? 3. So 3 is propane, so propane, and then ONE, propanone, right? Or you can write 2-propanone, just to give the number on which location you have a carbonyl group. So 2-propanone. Let's try question number B. So over here we know this is carbonyl group and this is ketone, because both that has carbon. So we have to give the lowest number, so we have to start from here. 1, 2, then this carbon is 3. I cannot go down because we have just one carbon. As we can see, if we go straight we could have 2 more, so we are going straight. 4, 5. So this is our parent chain, so the name will be 3-methyl, and then we have 5 carbon, 5 is pentane, and this is a ketone, that's why it's pentanone. So 3-methyl pentanone. Let's go to the C. This is the same type of question, same question that we already did. So 1, 2, 3, 4, 5. I already explained why this is a ketone. So the name will be 2-methyl cyclohexanone. Right. Okay. So this is the solution that I already explained how to name this ketone, all the example of the ketone molecule, that, and you can also read from here. So this is again the part of the solution that is given for you. So let's try to do some more example of naming of ketone. So let's try this problem. If you have so this is one of the problem. Second one we can have as okay. So now let's try to name like name both of these molecules. So let's start. The time I see is a carbonyl group, and we know this carbon group is attached to both the carbon, so we know this is a ketone group. So we have to start counting from this end. 1 2 3 4 5 6 7, and we're going to name as 4 6. We have 2 bromo attached as a substituent, so 4,6 dibromo, and we have 7 altogether carbon in our parent chain, so 7 is heptanone. So 4,6 dibromo heptanone. So this is our name for the first molecule. Let's do the second one now. So again, this is a ketone molecule. I already explained in the previous example, this is a carbonyl group, both sides has a carbon attached to it, so this is a ketone. And this is a cyclo compound. This is a 5-member ring, right? This is a cyclo compound. So give the preference to the carbon that has the carbonyl group. Now you have a choice, either you can go up or you can go down. So if I go up, the second carbon has the substituent methyl group. If I go down, second carbon has a substituent as a methyl group. So it doesn't matter for this particular case which way you're gonna go. So I'll go clockwise. So this is 2, this is 3, this is 4, this is 5. So how are we going to name it? We're going to name 2,5 dimethyl, because we have methyl group on both sides, and we have 5 carbon, and this is a cyclic compound. We have to write cyclo, and then we have 5 pentanone, right? Because this is a ketone, right? But if I had a same type of question, let's say 3, exactly the same type of question, C double bond O, you have CS3 in here, and you have CS2 CS3 in here. So how are we going to name this molecule? Exactly the same, I just changed the second substituent. In this we have ethyl, over here we had methyl, right? So how are we going to number this molecule? So let's start with 1 over here, 1. Now if we go down, we have a methyl group again. If we go up, on the second we have a methyl group, but both the substituent is occurring on the second carbon. But what's the difference? Now we have a tie, so we have to use a rule called alphabetical rule. So you have to use that rule and then figure it out which way you have to go, or which substituent you have to give the preference, right? So according to the alphabetical rule, you have to give the preference to that substituent that comes first in alphabetical order. So E comes first, in then methyl, the word. So we have to give the preference to the ethyl. So we have to go up 2, then 3, 4, 5. So make sure you know the difference. So the name will be 2-ethyl, then 5-methyl, cyclo, we have 5-pentanone, right? So this is the name of this third molecule. Okay, so make sure you practice this type of question, and let's go to the next slide. Now let's talk about the physical property of an aldehyde and ketone. So the physical property is whether this compound can be soluble in water solubility, and the boiling point and melting point, right? So let's see the structure of aldehyde and ketone. If this is an aldehyde and this is a ketone, right? If we can see, we don't have any hydrogen attached to the oxygen atom in both of them, in aldehyde and ketone. And if you remember, I told you, if you have to make a hydrogen bond, you have to have a hydrogen attached directly to the electronegative atom, right? But in this case we don't have anything, so that means this aldehyde and ketone doesn't form any hydrogen bond, right, with themselves. That's why the boiling point of aldehyde and ketone is lower than that of alcohol. If you remember from the alcohol chapter, alcohol can make a hydrogen bond with another alcohol molecule, but this is not the case for aldehyde and ketone because it doesn't have any hydrogen attached to the carbonyl group. So that's why it has a lower boiling point. Aldehyde and ketone has lower boiling point than compatible alcohols, and it has the higher than that of alkane due to difference in polarity. So that means alcohol has the highest boiling point, then you will have aldehyde or ketone, and then at the end you will have alkane. Then is alkane. Okay. So why aldehyde? We already know why alcohol has high boiling point, because it can make hydrogen bond, where aldehyde and ketone cannot form a hydrogen bond, right, within another molecule aldehyde ketone. But why aldehyde and ketone has higher boiling point than alkane? Because in alkane we doesn't have any functional group, but in aldehyde we have a carbonyl group, and because of the carbonyl group and because of the electronegativity difference between oxygen and carbon, you will have some partial charges. So this bond is polar, right? So it can be a little bit more soluble compared to the, or it can form a bond called polar interaction, polar interaction, which is not available in alkane. So that's why the boiling point goes like this, the sequence: alcohol is greater than aldehyde ketone, and then aldehyde is greater than alkane in boiling point. So now let's talk about whether this aldehyde and ketone can form a hydrogen bond with water, or is water soluble or not. So if we already know the carbonyl group doesn't have any hydrogen in both of them, but water has a hydrogen atom attached directly to the oxygen, right? So that means this hydrogen is capable of hydrogen bonding. If they can see any electronegative atom, whether it's oxygen, nitrogen or fluorine nearby, they can form water. Hydrogen can form a hydrogen bond with one of these atoms, right? So if I have an aldehyde group, if I put water nearby it, the hydrogen of the water and then oxygen from the aldehyde group or the carbonyl group from the aldehyde can form a hydrogen bond, right? So this is a hydrogen bond. Similarly for ketone, exactly the same reason. Hydrogen from the water can form a hydrogen bond from the oxygen of the carbonyl group. So that means this result in the water soluble nature of aldehyde and ketone. So that means aldehyde and ketone can be soluble in water as long as they don't have any large number of carbon atoms in the molecule, right? So the smaller aldehyde and ketone can be soluble in water because of this hydrogen bonding. So now let's talk about some of the chemical reaction that aldehyde and ketone goes through or normally shows. So the first reaction is oxidation reaction that we're going to talk about. So what is oxidation? How you going to produce or make an aldehyde? If you remember from the alcohol can produce aldehyde, if you remember. So primary alcohol, when you do oxidation, we can use KMnO4, potassium permanganate and potassium dichromate as an oxidizing agent. If I do oxidation of the primary alcohol, we normally get an aldehyde, right? So this is how you normally make aldehyde. Even though this reaction doesn't stop at aldehyde stage, it just goes, or it just keep on going and then produce carboxylic acid at the end. But if somebody asks you what's the oxidation product and how you're gonna make an aldehyde, is from the primary alcohol always, right? Similarly, how you're going to make a ketone? If you remember, the secondary alcohol, when you oxidize, you make a ketone, right? Because secondary alcohol has an OH group on the middle carbon, and if you oxidize, you will make a double bond, right? Which is this, that becomes a carbonyl group, right? So remember this thing, and then the ketone cannot be oxidized anymore. So we already talked this in the alcoholic chapter, right? That the ketones are less susceptible to further oxidation, right? And what about, okay, so let's do couple of example how you're going to make a compound. So like I said, difference in the reactivity toward oxidation is the chief reason why aldehyde and ketone are classified in separate family. What does it mean? Aldehyde can be oxidized to a carboxylic acid, where ketone you cannot oxidize ketone. So because of this chemical reaction differences, ketone and aldehyde are normally placed in different groups. Because of this oxidation, they give different product during oxidation. So let's take one of the example. This is benzyl aldehyde. You have benzene, you have aldehyde group. So benzyl aldehyde, when you do oxidation, so aldehyde goes, so whenever you do oxidation for aldehyde, it forms carboxylic acid. And you're gonna learn about this group, functional group, later in the chapter, right, in the coming chapter. So carboxylic acid has a functional group is like this. You have a carbonyl group, and then on carbonyl group you have OH attached. So this is your carboxylic acid group, or over here you have carbon, right? And then what's aldehyde? Aldehyde group is C double bond O, and then you have hydrogen, right? So let's take this example, benzaldehyde. You do the oxidation reaction, now it becomes a carboxylic acid group. The aldehyde group changed to carboxylic acid. And then you will learn later on how you name a carboxylic acid containing compound. You will learn later, but right now just remember this thing. This is a benzoic acid. So but later on we're gonna learn how to name any carboxylic acid containing compound. But in this particular example, our aim is to figure it out what's the product when you oxidize aldehyde. So it always a carboxylic acid product. So let's do the second one. Example, this is a ketone. We know this is ketone. The common name is acetone, and the IUPAC name is 1,2,3. This is 2-propanone. This is an IUPAC name, right? If I oxidize ketone, there will be no reaction. So make sure you know the difference. If I ask you anything, what will happen if you oxidize a ketone? There won't be any reaction, right? So let's take a couple of more example on the oxidation of ketone or aldehyde. Let's start with a ketone. If you have this compound, and if you oxidize it, if you do the oxidation, oxygen, what's gonna be your product? The time I see this is a ketone, I'll just write no reaction, because this is a ketone, right? What about this? If I do oxidation, again no reaction, because this is a ketone again, right? But if I have something like this, if I do oxidation, what should be the product? This time this is not ketone, this is an aldehyde. So if you figure it out, this is an aldehyde, you know this is a carboxylic acid. OH. So this group is carboxylic acid group. Right? So you're making a carboxylic acid. If I give you one more question, if you have an alcohol, if you do oxidation, I know this is an alcohol. If I do oxidation, what should be a product? Alcohol goes to aldehyde. So this will be my product. This is your aldehyde. But this reaction won't stop on aldehyde. This is your aldehyde. This is your alcohol. And which type of alcohol you have? Primary alcohol. Right. And then the reaction won't stop in aldehyde. It will keep on going until you get a carboxylic acid. Right. So these are the examples that you need to have in your mind, how you're going to figure it out, which type of chemical reaction is going on, which type of product you're going to get if you oxidize any aldehyde or ketone. And then how you're going to get an aldehyde and ketone. Primary alcohol will give you aldehyde, and then later carboxylic acid. Secondary alcohol will give you a ketone that won't further oxidize. Right? And what about the tertiary alcohol? So if I have, let's say, the fifth question, if I'm putting over here, if this is the alcohol, if I oxidize, what you're gonna get? Whether you're gonna get aldehyde or ketone. If you oxidize this is a tertiary alcohol. And if you remember from the previous chapter, you won't get any aldehyde or ketone. There won't be any reaction on the tertiary alcohol. So keep this in mind, which type of alcohol give you which product, right? That will be really helpful. Okay, so now let's talk about some of the chemical reaction. So there are a couple of reagents that we normally use to figure it out the presence of an aldehyde. So that means if I give you any solution, how you going to figure it out this solution belongs to either ketone or aldehyde? How you going to determine? So there are two tests or two reagents to figure it out the presence of an aldehyde, specifically aldehyde. So the first reagent or first test that we're normally going to do is tolerance reagent. The second test is Benedict reagent. So these two reagents normally test for the presence of an aldehyde. Right. So let's talk about the tolerance reagent. What is tolerance reagent? Tolerance reagent is a mild oxidizing solution that contains a silver ion. So what does it mean? Like I said, this is a mild oxidizing agent, means it oxidizes aldehyde. If there is an aldehyde present in a solution, it's gonna be oxidized to a carboxylic acid, right? And the silver ion is going to reduce, right? So this is an aldehyde. Let's say this is one of the aldehyde that is present in your solution. You have to put a tolerance reagent. Tolerance reagent contains silver ions. If you did see over here silver ion, then what should be a product? A carboxylic acid. This is a carboxylic acid, and then the silver ion is going to reduce to silver. So this is how you normally figure it out whether you have an aldehyde or not in the given solution, right? The main thing is in tolerance reagent is this: if you carry out this reaction in a clean, grease-free glass container, if you carried out all this reagent test in a clean grease-free glass container, you will see this silver is going to be deposited on the side of this container. Silver, so it's gonna deposit over here, and then sometimes this deposited silver glass container we normally use as a mirror, right? So during the chemical test in the lab, you will see a mirror like thing is appearing on the inside of the glass container because of the deposition of silver atom on the inner surface of the glass container where the reaction is going on. So you can easily see whether the reaction is already done or not. The second reaction is Benedict reagent. So Benedict reagent is also used as a mild oxidizing solution in which we use copper ion, Cu2 plus ion. So the difference is in tolerance reagent we're gonna use silver ion, in Benedict reagent we're gonna use copper ions. And so we're going to figure out whether the solution has aldehyde or not. So this is one of the example of aldehyde. You have aldehyde group and we use a copper ion, and this copper ion has a blue color. So before reacting the copper is blue, but if you have an aldehyde group in a solution, this will react with aldehyde and this aldehyde will oxidize to carboxylic acid again, and the copper is going to reduce to Cu2O cube, right? And this is a type of product that will give you a red precipitate. So that means if your solution is turning from blue to red, that means you have a aldehyde in the solution, right? So make sure you know the difference. In tolerance reagent you will get a grease free silver ion deposit on the glass container, so that you can that can be seen as a mirror, whereas in Benedict reagent the blue solution of the solution after the reaction is converted into a red precipitate, and this red precipitate is a positive sign that tells you have an aldehyde group in the given solution. Okay, so we already done with both this test. The important thing is over here, ketone won't give any positive test with these two reagents. So remember this thing, ketone cannot give any of the positive tests with any of the reagent, both the reagent that we discussed. So that's why you can differentiate between aldehyde and ketone in a given solution. So like I said, ketone cannot give the reaction with tolerance reagent or Benedict reagent test, but there is some special characteristic of aldehyde. So so remember this thing, tolerance reagent test is given by all aldehyde, right? If you have an aldehyde group, tolerance reagent will give positive test, but for Benedict test only certain aldehyde will give you a positive test. And this test, Benedict test, can be given out by one ketone, but you have to have some special structure attached to this ketone. So I'll explain you how this ketone is. Some ketone can give Benedict test, or some ketone containing compound. So what are the three structural features that you need to have in an aldehyde group so that can give a positive Benedict test? So the first of the requirement is, if any aldehyde group has a carbonyl group attached next to the aldehyde group, that aldehyde compound can give a positive Benedict test. Second structural thing, if you have an aldehyde group and for aldehyde in the next adjacent carbon you have to have an OH group, alcoholic group, attached to the adjacent carbon, that aldehyde group can give a positive Benedict test. The third one, this is a ketone, so only that ketone give a positive Benedict test that has the OH group attached to the adjacent carbon. If you don't have this OH group, this ketone cannot give Benedict test. But the time you put OH group next to the ketone, that will give you a positive Benedict test. So only these three structural features can give you a Benedict test. Two of them an aldehyde with a required structural feature, and one, the last one, is your ketone with a special structural feature that you have an OH group on the adjacent carbon. So make sure you know the difference which type of compound can give Benedict test, right? So I already explained which type of ketone give you a Benedict test too. Right? Simple ketone cannot give Benedict test, only a special one which I already described over here. Okay, so now on this slide we're going to talk about one more chemical reaction given out by aldehyde and ketone, which is addition of hydrogen. So if you remember from the previous chapter, I told you whenever you add any hydrogen to the compound, that means we are doing a reduction reaction. Right? Like we have oxidation reaction where you normally oxidize in the presence of oxygen. In reduction, we normally add hydrogen. In oxidation, we add oxygen. In reduction, we add hydrogen, right? So aldehyde and ketone are reduced to alcohol by the addition of H2. So let's take one example. This is an aldehyde group. I know this is an aldehyde. If I put H2, so you're gonna get what? So you're gonna put one of the hydrogen over here, and out of the two hydrogen, one of the hydrogen goes to this carbon, right? So one each across the carbonyl group. If you can see over here, one goes to the oxygen, one goes to the carbon that contain the oxygen bond, right? And you always produce a primary alcohol, right? So if you remember, this is a reduction reaction in the presence of a catalyst called platinum, right? So when you reduce an aldehyde, you're gonna get primary alcohol. But how you gonna get aldehyde? If you oxidize it, right? So this is a back and forth reaction. So aldehyde, if you reduce it in the presence of hydrogen, you get primary alcohol. If you oxidize primary alcohol, you're gonna get aldehyde. So this is a back and forth, right? Similarly for ketone, if you remember, you always get ketone when you oxidize a secondary alcohol. So that means when you reduce the ketone, you're gonna get secondary alcohol, right? So again H2, put one hydrogen over here, put one hydrogen over here, then you're gonna get secondary alcohol, right? Again, ketone, when you add hydrogen, you're gonna get secondary alcohol. If you oxidize secondary alcohol, then you're gonna get ketone. So this is the back and forth reaction again. So let's take a couple of examples of this reduction of aldehyde and ketone. This is propanol with an aldehyde group. When you add hydrogen, what should be a product? It should be an alcohol, and the alcohol will be primary alcohol because this is an aldehyde. So the time is, this is primary alcohol. Put one hydrogen over here, put another hydrogen over here, then you will get OH group, right? And the name will be 1-propanol, and this is a primary alcohol. This is ketone. This is 2-propanol. Common name is acetone. When you reduce in the presence of platinum by adding hydrogen, you're gonna get, because this is a ketone, you're gonna get secondary alcohol. Put one hydrogen on the top, one hydrogen on the bottom, you're gonna get secondary alcohol. So by looking, or if you know which kind of functional group you have, aldehyde or ketone, you know what should be the reduction product, whether it's primary or secondary, right? By looking which functional group you are reducing, whether it's aldehyde or ketone, right? So let's try a couple of example of reduction and then try to make a product. So the first one, when you add hydrogen in the presence of platinum, right? second one, the third one, okay. So let's try to make or to solve the first one. So which type of functional group you have? You have carbonyl group, and then the carbon group is the carbon that has the carbon group is attached to the carbon on both sides. So this is a ketone group over here, right? So if this is a ketone, if I reduce it, what should be our product? It should be a secondary alcohol, because that secondary alcohol, when we oxidize, we're gonna get this ketone, right? So let's try this one. This is oxygen. Put one hydrogen over here, but I won't show you the second hydrogen because this is a line angle formula, but make sure you assume that you have one hydrogen. The second hydrogen goes to this carbon, right? So this is a secondary alcohol, right? So, and you make sure you also have to name the reactant as well as the product. So let's name the reactant. So let's start from a 1, 2, 3, 4, 5, 6. What should be the name of the reactant? Is 3-hexanone, right? This is a ketone. And once you reduce 3-hexanone, what should be the product? You already made the product, but what's the name of this product? Again, 1, 2, 3, 4, 5, 6. Then the name will be 3-hexanol, right? So make sure you practice this type of thing. Make sure you know how to name it. So let's do the second thing. Second product, your thing is benzaldehyde. Then you're gonna make, this is an aldehyde, if you reduce, you're gonna get primary alcohol. This is OH, this is H, right? So the main reaction is like this, CHOH. So this is a primary alcohol. Let's do the third one. This is an aldehyde. So if this is an aldehyde, again, what should be the product? Primary alcohol again, 1, 2, 3, 4, 5. Then this is OH, right? So what's the name? 1, 2, 3, 4, 5, 6 hexanal, Al, or 1-hexanal. The name will be 1-hexanol, because this is alcohol, right? So make sure you practice this thing and make sure you know how to name reactant as well as the product that you're gonna make. And now we're gonna talk about two terms, hemiacetals and acetals, as well as you will learn in the next couple of slides what are ketals and hemiketals, right? So we're gonna learn what are hemiacetal, how we're gonna form this hemiketals, ketals, hemiacetals and acetals. So we form hemiacetal and acetal when aldehyde react with an alcohol. So that means, what is aldehyde? This is R, C double bond OH. This is your aldehyde group. When it react with an alcohol, it form, this is a reversible reaction. First you will form hemiacetal, but if you have enough amount of alcohol present, then the hemiacetal is going to convert into a acetal group. So this is the reaction that we're going to follow and learn how this what is hemiacetal and acetal is, and how does the structure looks like. So like I already told you, hemiacetal and acetal form when aldehyde react with an alcohol. Then you will form hemiacetal that are not very stable. So this hemiacetal part is not stable, right? And they are difficult to isolate. So that's why when the reaction goes through hemiacetal, they can come back to its original reactant, which is aldehyde and alcohol, or if we have enough alcohol, this hemiacetal is converted into an acetal part, which is a stable one, which you can isolate. So depending on the amount of alcohol present or that can react with an aldehyde, you can have acetal or you can have hemiacetal. So how does the hemiacetal looks like? So this is the structure. If you have the carbon, and on the same carbon you have alcoholic group as well as ether group. This is your ether, this is your alcohol, and this is your hydrogen. And this bond can be any R group, any alkyl group. So the carbon that has OH group, the same carbon will have an ether group and the same carbon will have the hydrogen. So if on one particular carbon you have all these three atoms attached, we call that carbon or that compound as hemiacetal. And now let's talk about acetal and how does the structure looks like. Exactly the same structure of hemiacetal, but the only difference is the OH is get replaced by another OR molecule or another ether molecule. So if you see a difference, the same carbon has two ether, so the OH is get replaced by another ether molecule, and then you have hydrogen atom. So that compound that has a carbon that has two ether molecule attached to it on the same carbon and one hydrogen atom, we call that particular group or that compound as acetal compound, right? We'll see how we can make this kind of product, which is acetal or hemiacetal. We'll see in the next slide how we can form this kind of product. So let's take an example. Let's talk about the general reaction, how this reaction looks like. So we're gonna start with an aldehyde and we're gonna start with an alcohol. So if we know in carbonyl group of the aldehyde, this is partial negative, this is partial positive, because oxygen is more electronegative compared to the carbon, and if an atom is more electronegative means that atom will have a partial negative charge, right? And then the one that is less electronegative will have a partial positive charge. So what's going to happen during this reaction? The RO group from the alcohol, because this is going to attach with the carbon of the carbonyl group, and the hydrogen is going to go with oxygen, and the one of the bond is going to break, and then you're going to get what? Alcohol, because the O is attached with the hydrogen, and you will get one ether, right? And then this is the hydrogen that is already been attached, and this is the R group that is already present on the carbon. So this structure is hemiacetal. If you can see the carbon, the same carbon has an alcohol, same carbon has an ether, and the same carbon is attached with the hydrogen. So this is the structure of hemiacetal. But if we have enough amount of alcohol, let's say if we have enough amount of alcohol, there won't be any deficiency of alcohol. This reaction won't stop in hemiacetal and react again with the alcohol and to form acetal. We'll see how in the presence of an acid. So now we have another alcohol. So the RO group from the alcohol is going to replace OH group. So it's a substitution reaction. I can say substitution reaction. So what are substitution reaction? Where one of the group is replaced by another group. So in this particular case, the hydroxyl group, OH group, is going to replace by RO group of the alcohol, and then you will see the OR group over here. and this OH group that is being replaced is going to react with the hydrogen of the alcohol and form as water. So now you will get this structure where the same carbon will have OR group, ether group, and again the same carbon you have again one more ether group, and then you have hydrogen attached to the same carbon. So that means this is acetal. So you have to know the structure of acetal, where you have two ether attached to the carbon and the third bond is attached to the hydrogen. So that compound is acetal. Whereas hemiacetal is the carbon on which one of the group is alcohol, another group is ether, and the third group is hydrogen. So that's your hemiacetal. So make sure you know the difference between hemiacetal and acetal. So let's take an example over here. You have aldehyde react with an alcohol. So what's going to happen? The CH3O group of the alcohol is going to attack the carbon of the carbonyl group, and the hydrogen is going to attach with oxygen, and this one of the bond is going to break because carbon can form just 4 bonds. So the top one is going to convert into alcoholic part, bottom one is ether, and the carbon that has both of these group attached to the hydrogen. So this is hemiacetal. But if we react this hemiacetal with one more molecule of alcohol, then what's going to happen? Then this CH3O group again from one more alcohol molecule is going to replace OH group. Is going to replace the OH group and then get attached on the carbon, which is this. Now you have two ether group attached to the same carbon and then one hydrogen, and the OH group that you had on the top is going to interact with the hydrogen of the alcohol and remove as water. Right? So this is an acetal because the same carbon has ether group, OCH3 OR group. Right? So it is diether group on the same carbon. Right? And then you have hydrogen on the third group on the carbon. So this is an acetal. So now let's see one more time what are hemiacetal and acetal. Like I already told you, for any compound to become hemiacetal, the carbon should be containing OH group, ether group, and hydrogen. All should be present on the same carbon. So again, alcohol part, ether part, and hydrogen should be present on same hydrogen. So this is hemiacetal. Whereas in acetal, the OH group is replaced by another ether molecule. That's the only difference. If you compare this part with this part, so OH is get replaced by an ether molecule, and you have one more ether, and the third one is hydrogen, and the carbon that contain all three group is called acetal carbon, and the entire group is called acetal. So now let's see, I already explained to you how does the hemiacetal and acetal normally form during the reaction of an aldehyde with an alcohol. So this is just one more explanation, exactly the same. The CO3 is going to bind with carbon, the hydrogen is going to attach with oxygen, then you're gonna form hemiacetal, right? So this is the same reaction or same type of reaction that I already explained to you how to make acetal from hemiacetal. So let me explain one more time. This is hemiacetal. Now we have one more alcoholic group, then the CH3O group from the alcohol is going to replace hydroxyl group, and this hydroxyl group is going to bind with the hydrogen of the alcoholic part and remove as water. And now this OCH3 group is over here on the carbon. So this is acetal. Why? Because you have two ether group one hydrogen on this carbon, right? The same carbon. So that's why this is acetal. And why this is hemiacetal? Because you have OH group and ether group. So you have two different group on the carbon, and the third group is hydrogen. So you have to know the difference between hemiacetal and acetal. So now let's talk about the ketone reaction. Like for aldehyde, we're gonna make hemiacetal. Let me write over here. For aldehyde, we're going to make hemiacetal and acetal when it reacts with alcohol. Whereas when ketone react with alcohol, it forms hemiketal or ketal, because it comes from ketone, so that's why it's ketal and hemiketal, right? As the name is already showing to you. So how does the hemiketal looks like? So before we go to the hemiketal, we should know what is the structure of ketone. So ketone is RC double bond O C. This is your ketone, right? Where the carbonyl group is attached with the adjacent carbons, right? Or I can write, instead of R, I can say C, right? C double bond O C. This is your ketone. So to make hemiketal, the ketone, the carbon of the carbonyl group should be attached with an alcohol, which is this, and an ether group. This is alcohol, and and the fourth carbon should be attached with one more carbon, right? But if you remember from the acetal and hemiacetal, the fourth carbon is normally attached with hydrogen, but in ketals it attached with the carbon, so you don't have any hydrogen attached to the central carbon over here. So this is the difference, and everything else is same. So you have OH and ether, alcohol in ether. That's why this is hemiketal. What does ketal mean? When the same carbon has two ether group, ether, and the third group is again carbon. There is no more hydrogen on this central carbon that has the ether group, right? So this is ketal. So it's exactly the same concept, but the only difference is you don't have any hydrogen attached to the carbon that has ether or alcoholic group. So let's see how we normally make hemiketal and ketal. So we're gonna use a ketone, react with an alcohol, then the RO part from the alcohol is going to attach with this carbon, and the NH part is going to go on this oxygen, and you will make, and one of the bond is going to break. That's how you're gonna make an alcohol. You're gonna make ether group, functional group, and then the third bond is already bonded to an alkyl group or carbon containing group. So if you can see, there is no hydrogen, that's why his name is hemiketal. But if you add one more molecule of alcohol to hemiketal, then this ORO group is going to replace the OH group, and then after getting replaced, this OH group is going to bind with the hydrogen of the alcoholic group and remove as water, and then you will get two ether group on this carbon, on the same carbon, and the third group is carbon again, alkyl group. So that's why this is ketal, because we know this comes from ketone. So let's take an example. This is ketone, this is one of the alcohol. Take this CH3CH2O negative, going to bind with here. The leftover hydrogen is going to go on this oxygen, the bond is going to break, you will get alcohol, you get ether, and the third bond is already bound to the another carbon, right? Because this is a ketone. So this we call as hemiketal. But if you have one more alcohol, this alcohol is going to replace this OH and it attach with the hydrogen, remove as water, and now you have two ether group attached to the carbon. And then the third group is attached with the carbon, because this is comes from ketone. How we know it's ketone? Because there is no more hydrogen attached to the carbon that has both ether group. Instead of hydrogen you have carbon, so that's why this is ketal. Right. Let's try to solve a couple of problems. So we're gonna make a product from the reaction given. So let's try the first example. If I have a benzene and you have this reactant, if it reacts with 2 moles of CH3 CH2 OH in the presence of an acid as a catalyst, so what should be a product? Now we have to do the second reaction. This is benzene, this is O, this is CH3. Again, in this case you are reacting with 2 moles of alcohol, which is methanol, in the presence of acid as a catalyst. So now let's try to solve what should be the product. So the time I see, this is an aldehyde, this is an alcohol, so we know if we aldehyde react with an alcohol, we're gonna get acetal or hemiacetal. So now let's try to solve this problem. Okay. So what we're gonna do, we have 2 molecules of ethanol. This is ethanol. So the first molecule of ethanol, this CH3O group is going to attack this carbonyl group, and the hydrogen from the first molecule of ethanol is going to go on this oxygen, and then you're gonna make a product something like this, OH, then you have hydrogen, then you have OCH2 CH3, and this is hemiacetal, right? So this is hemiacetal, and now again the second alcoholic molecule, because we already used, out of the 2 we already used the one alcoholic molecule to make an hemiacetal. Now the second alcoholic molecule that is present will do again the same reaction. This CH3 CH2O negative O is going to replace this OH group from the hemiacetal, and the hydrogen is going to bind with this OH and remove as water. So what should be the reaction now? So the reaction will be from hemiacetal and then you're gonna get water as your byproduct, right, which comes from OH and H, right, together as water, and then we're gonna make acetal. So these are the product that we're gonna get when we mix an aldehyde, benzene aldehyde, react with 2 molecules of ethanol. So when one molecule of ethanol react with an aldehyde, you're gonna get hemiacetal, and when another molecule of the alcohol react with hemiacetal, you're gonna get a complete acetal. So let's do the second one. Again, you have two molecules of ethanol, means you have two molecules CH3OH, CH3OH. So if you use the first CH3OH, this CH3O is going to bind with this carbon and the hydrogen is going to go on this oxygen, and you're going to make then you're going to make OCH3, and then you're going to make OH, right? This H is this one, and this CH3OH is going to come over here. And then let's see whether this is acetal or hemiacetal or ketal or hemiketal. This carbon has an OH group, the same carbon has OH3, OH ether OCH3, and the same carbon is attached with another carbon. So this is ketal, but this is hemiketal, right? And if I use a second molecule of alcohol again, then what's going to happen? This CH3O is going to replace this OH group, and this hydrogen is going to bind with the OH group and remove as water, right? And then you will get the product something like this. OCH3, which is this one, and you have OCH3, CH3. So this is ketal. Right. So this is the product that you're gonna make, and make sure you practice this kind of reaction too. So now let's try to solve a couple of problems on identifying the functional group. So out of the 4 examples that is given on this page, we have to classify or say which one is hemiacetal, which one is hemiketal, acetal and ketal. If there is none of them, we need to write none of the above. So let's focus on the first example. If we see this OH group, alcoholic group, attached on this carbon, this OR group, which is ether group, is present on another carbon or a different carbon, is not on the same carbon that has the OH group. So that means it's not following any of the rules that classify as hemiacetal, hemiketal, acetal or ketal. So that means the answer is none of the above. Because to be treated as hemiacetal, hemiketal, acetal or ketal, what you need to have, you have to have on the same carbon, you have to have OH group, OR group, then you have any R group, and then if you have an H, that is hemiacetal. If you have C, then it's hemiketal, right? If I remove this OH and put one more R on the same carbon, then this is ketal. And then if I remove this hydrogen carbon and replace with hydrogen, then it's become acetal, because comes from the aldehyde part and they have ether group. So we already know what are the concepts to figure it out which one is out of the 4 group that is given, right? So let's go to the part B. This carbon has OH group attached, the same carbon has OR group attached, ether group. This is alcoholic group. So in this particular case, the same carbon as alcohol, same carbon is attached to an ether, and the same carbon attached to a hydrogen. The time I see hydrogen, we know this is aldehyde, so it has to be acetal, but we have to figure it out whether it's complete acetal or hemiacetal. This is hemiacetal. Why? Because one of the group is alcohol, it's not the ether. This is not diether group on the same carbon, so that's why this is hemiacetal. Let's take the third one. This carbon has OR group, ether group. The same carbon has another OR group, ether group, but the third one is not hydrogen, this is carbon. So the time I see the third bond attached with the carbon, not with hydrogen, we know this comes from ketone, because ketone is the only carbonyl group where you have carbon carbon across the carbonyl group. So that means it has to be ketal, but we need to know whether it's hemiketal or complete ketal. So by looking at the structure, we have two ethyl group attached to the same carbon, so this is ketal. If it was one of the groups, let's assume is OH alcohol, then it become hemiketal. So now let's go to the D part. So over here, this is the carbon. The same carbon has OH group, same carbon has OH3 group, that means alcohol, ether, right? And the third bond is attached with, again with the carbon, right? So there is no hydrogen attached with this carbon, center carbon. So that means it's come from ketone, but one of the group is OH group, so that means this is hemiketal. Right. So make sure you practice this kind of problem to figure it out which kind of groups you have in the given organic compound, whether it's ketal, hemiketal, hemiacetal or acetal. So this is the solution that is already given to you, so you can have a read, and then because I already explained you why all those four are ketal, hemiacetal, whatever I wrote it down in the previous slide, I already explained to you, so you can just write it down, more information. So this example is again the same. You can read it out and then see why the name of the why the name is given for one particular organic compound. So you have, again, this is a solution from the same question. So now we're gonna talk about a special type of hemiacetal or hemiketal called cyclic hemiacetal or cyclic hemiketal. The time I know this is cyclic, we know it's a closed circular ring of 5, 6 carbon, right? 5 carbon, 4 carbon. So why some compound form cyclic hemiacetal or cyclic hemiketal, but some form open form of hemiacetal and hemiketal that we just learned. So how would you know that which compound can form cyclic hemiacetal and cyclic ketals, hemiketals? So if we can see over here, let me give you one example. If I have one compound that has C double bond OH, CS2, 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 and then OH. What's special about this compound that I just wrote it down? Over here, within the same molecule, we have aldehyde group. If you can see, this is aldehyde, and within the same molecule I have what? Alcohol. And if you remember from the previous slide, how we normally make any acetal or hemiketal or hemiacetal? When aldehyde react with alcohol or when ketone react with alcohol. So if we take a first example, in this case aldehyde and alcohol is present in the same molecule, they can react within the same molecule, right? So this kind of interaction we normally call as intramolecular interaction. Intra means within the same molecule, right? So let's take the same example. I can write the same structure like this: CS2, 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 1, 2, 3, 4, one more CS2, and then OH. I can draw the same structure like this, exactly the same. You have same number of carbon, you have an aldehyde group, you have OH group, right? So what's gonna happen? If you remember from the previous reaction, this OH from the alcoholic group, this oxygen is going to attack this carbonyl carbon. That's what we learned from the previous example, right? And this hydrogen, leftover hydrogen, is going to go with this oxygen. And then what you're going to form? You're going to form something, this kind of structure, right? Because the time this oxygen attack this carbon and make a bond, you are going to make a cyclic compound, right? In which how many atoms you have? You have 1 carbon, 2 carbon, 3 carbon, 4, 5, and then 6th atom, and the 6th atom will be oxygen. So if you have 6 atom, out of the 6 atom you have 5 carbon and 1 oxygen, what's the main cyclic structure you can form? Can you form a 6-member ring where one of the atom is oxygen and all other are carbon? This is carbon. I can make this structure like this, and on this carbon you have OH group attached and hydrogen attached. This is the same structure that is drawn on the PowerPoint. Getting my point? So once, let's assume this hydrogen, when it went and attached with this oxygen, this bond is going to break, and what you're going to have? You're going to have OH over here, the alcoholic part, and the hydrogen is going to remove from here because it's already gone, right? And the same carbon will have hydrogen. So this is the hydrogen, this is the alcohol that is made over here, right? And then this is the same oxygen that you have in a 6-member ring, right? So how would you know this structure, cyclic structure, is a hemiketal or hemiacetal? Because we started with an aldehyde, right? We started with an aldehyde, so that means it has to be an acetal, but we have to look whether it's complete acetal or hemiacetal. How would you know that? We have to see the carbon. This carbon has an OH group, this carbon has OR group, ether group, and the same carbon has hydrogen. So that means because you have alcohol, you have ether, that means this is hemiacetal. Because to become complete acetal, you have to have 2 ether group attached to the same carbon, right? So this structure is cyclic hemiacetal. So let's take one example, and this cyclic acetal or hemiacetals are important in carbohydrate chemistry. So when we're going to talk about carbohydrate, you will see this kind of structure we're going to talk about. So let's take one example and see how does the reaction goes. This is cyclic hemiacetal, right? When 1 more extra alcohol is given, or if you do a reaction with 1 more alcoholic molecule, what's going to happen? This CH3CO group is going to replace this OH. So this compound is going to bind with this carbon, and this OH is going to get removed and react with this hydrogen and remove as water. So the OH and H completely react to remove as water, and this CH3O is going to attach with this carbon. So now you will have this ether group. Now you have 1 more ether group, and the third one is hydrogen. So that means this is cyclic acetal, because you have 2 ether group on the same carbon, and you have the third one as hydrogen. So this is cyclic acetal, because this is a cyclic compound, right? So let's do one more example to figure it out which one is cyclic hemiacetal, cyclic hemiketal, or cyclic acetal, or cyclic ketal. So let's try with the first one. So this is the carbon. This carbon has an OH group. This carbon has ether group. This is alcohol group, and the same carbon has one more carbon attached to it. So that means we don't have any hydrogen attached to the carbon that has alcohol and ether. So that means it comes from ketone. If it comes from ketone, it should be ketal, but this is hemiketal because you have an alcohol, you don't have any 2 ether group. So this is hemi. Let's do the part B. This is the carbon, you have an ether group attached to this carbon. You have one more ether group attached to the same carbon, and the third group is attached with the carbon. So again this comes from ketone, and then we have 2 ether group attached to the same carbon. That means this is ketal, complete ketal. And let me, this is cyclic hemiacetal, this is cyclic ketal, right? Because it's a cyclic compound. Let's talk about the third one. This carbon has an ether. This same carbon has one more ether, OCH3, but in this case the third bond is attached with hydrogen. So that means it comes from aldehyde. And you have diether on the same carbon, ether. So that means this is cyclic acetal because it comes from aldehyde. Let's do the fourth one over here. Same carbon has alcohol, same carbon has ether, and the third bond is attached with hydrogen. So the time I see hydrogen, we know this comes from aldehyde, but in this case one of the group is alcohol and another group is ether, so this is not complete. So I can say this is cyclic hemiacetal because it comes from aldehyde. So this is how you can verify whether the cyclic compound is ketal, hemiketal, acetal or hemiacetal. So this is the solution that I already explained you how to figure it out whether it's cyclic acetal or cyclic hemiacetal, but you can have a look over here and then again you can practice by reading out all the notes that is given on the PowerPoint. So now on this slide we're going to talk about the hydrolysis of aldehyde and ketone, right? So what is hydrolysis? Is the breaking of bond in the presence of water. In the presence of water, right? Hydrolysis, bond breakage by reaction with water. So acetals and ketals are stable but may be converted back to an aldehyde and ketone through acid catalyzed hydrolysis. So whenever you do acid catalyzed hydrolysis, the acetal as well as ketal is going to convert into respective aldehyde and ketone and alcohol, right? So let's take an example of general reaction of acetal hydrolysis. This is acetal. Why this is acetal? The same carbon has one ether group, another ether group, third one is hydrogen. So this is complete acetal group, right? And we know this acetal comes from where? When we reacted aldehyde with alcohol. When we react aldehyde and alcohol, we get this acetal, right? So if we break the bond and if you do the hydrolysis, which product you are expecting? You're gonna get exactly the same product from which you get this acetal, right? So remember, whenever you do hydrolysis, you're gonna break this bond, and put hydrogen across it. That means you're gonna get alcohol. That means 2 molecules of alcohol. And then once you're breaking the bond, so that means how many bond carbon need? Carbon need 4 bond, 1 bond is over there, 1 bond is over there, but the carbon still need 2 more bond. So just put double bond O, carbonyl group, which is this. And now you're gonna make an aldehyde. So this is how we are not going to go in depth into the reaction mechanism. How does the reaction mechanism work? But you can just break the bond and get the alcohol and then put carbonyl group, C double bond O group, on the carbon that has ether group. Right. Let's take one more example. Again, this is ketal. Why? Because you have ether, and then you have one more R group. So this comes from ketone. That's why this is ketal. So then you're going to perform the same concept. You have to break this bond. You have to break this bond, and then you have to put hydrogen from the water. Right. So the hydrogen is coming from water. So now you're gonna have two alcohol molecule. And then the time you break this bond, you have to give two more bond to this carbon. So that's why you have to put double bond O. This comes from this oxygen from the water, right? So this is, you have carbonyl group, and then this is ketone, and this is alcohol, right? So let's take an example. So which molecule is this one, ketal or acetal? So the time I see carbon, you have an ether, you have one more ether, and then the third bond is again with the carbon. So we don't have any hydrogen. That means it comes from ketone. So this is complete ketal, because you have two ether group, right? So that's why it's only ketal, not hemiketal. And now we're gonna see how does it react in the presence of water. How does this hydrolysis mechanism work? Break this bond, you're gonna break this bond, you're gonna break this bond, and now you have to put one of the hydrogen over here, one of the hydrogen from here, from the water, and you're gonna take out this entire alcoholic part. So you're gonna get ethanol, right? Because you have two carbon and this is alcohol, and you have two molecule, because one of the molecules comes from the top, one of the molecules comes from the bottom. And now after you break two bonds on the carbon, you have to provide two bonds. So you have the leftover oxygen from the water, and then provide double bond O to the carbon. So that means you are making a carbonyl group, and this is ketone, and then you can write this is ketone, right? And then you can write this is 2-propanone, because this is 3 carbon. Right, so this is how you normally do a hydrolysis reaction and make a product. Let's take one example of hydrolysis. So this is the molecule. We have OCH3, and when we do a hydrolysis in the presence of an acid, what we're going to do, we have to break this bond, and put one hydrogen, and this hydrogen come from water, and then this carbon that has the 2 ether group is already, the bond is already broken. Then this oxygen is going to bind with this carbon, and you're going to make two molecule of CH3OH. One is this, one is this, and you're gonna make ketone. So make sure you practice this type of question.